All right, now let's talk about underspecification of a model. And here we're dealing with omitting a relevant variable. And again, as the previous time, what is relevant? Relevant means that it has something to do with y, with your dependent variable. So if I omit that relevant variable, what will happen to the unbiasedness of my estimator and what will happen to the variance? And guys, remember, there is always trade-off between the two. Okay, we cannot have them either in both ways. So in the ideal world, yes, we want to come up with some variables and estimate the coefficients for those variables that they are both unbiased and the variance is small. But in real world, there's a trade-off between the two. If you want to have unbiased estimator, you have to make sure that I don't know, you cannot have both a small variance and unbiasedness at the same time. So that's the idea. Now let's see what will happen to those things if I omit that relevant variable. Imagine x2 as a relevant variable in this model. Again, the model is a very simple one. Y is equal to beta 0 plus beta 1 x1 plus beta 2 x2 plus u, right? This is a true model, and the true model contains x1 and x2, right? If I knew for a fact that this is a true model and I had all the observations for x1 and x2, in other terms, the x1 and x2 were observable, or I could collect data for them, then I would say that this was the true estimated version of the model, right? I have to include both x1 and x2 in the model. So using Venn diagram, this is my y, this is x1, this is x2. And look at that, both of them are relevant. And specifically here, we want to drop one of them. Let's drop x2 and see what will happen. And again, it is relevant. It means that there's some relationship between x2 and our y. You see there's overlap between x2 and y. Okay. Now let's say, because of some reason, let's imagine due to our ignorance or data availability, then this estimated model x2 is omitted, and this one, actually this version, is used to estimate the true model. So imagine I know this is ideal, but this is what we do in practice. So in practice, imagine we use this one. And if you're wondering why I dropped this x2, sometimes you have to. Imagine going back to our example of wage versus education. Imagine this was the example. Y is wage and beta 0 plus beta 1, education plus beta 2, ability plus u. So this ability, we don't have data for ability, right? But we know it's something very important in terms of explaining your wage. So yes, in real world, in hypothetical true world, we love to have this ability in the model, but in practice, we cannot have that ability in the model, so we drop that. So again, this is your wage, this is your education, this is your ability. So let's drop this ability from the equation and see what will happen. Okay. In previous classes, we already discussed that. If we do that, it's going to make our estimator for education, the estimate for education, to be biased, right? But now let's see what exactly is happening behind the scene and answer this question: is there any problem using Venn diagram? For that, I'm going to go back to the whiteboard and walk you through the example. Okay, so we already talked about the overspecification. Now let's talk about underspecification using Venn diagram. This is my y, this is x1, and this is x2. If that's the case, then OS is going to use this part of the data, call it beta hat 1, this part of the data, call it beta hat 2. Okay, beta hat 1, beta hat 2. Okay, and actually let me remind you that where am I using hat versus tilde? You see, the ideal model, we're gonna reserve hat for those. So beta hat 0, beta hat 1, beta hat 2, and the one that we're using in practice, we show it with tilde, right? Beta tilde 0, beta tilde 1, right? Again, these are just names and arrangement. Don't get stuck there. Just let's say in this example, we're going to use hat for the ideal model. We're going to use tilde for the one that you're using in practice, right? So this is the ideal case. Beta hat 1, beta hat 2, both of them unbiased. We're happy. Now let's see what happens if I drop this x2? If I drop this x2, what will happen? Okay. Okay. I want you to think about it. Just ignore this dash line because we are dropping them. If I drop them, then how OLS is using the coefficient for beta 1? OLS is going to use all the information here. Again, remember, we are dropping x2. So OLS is going to use all that information, and we call it beta tilde 1. Do you remember? So this was the not ideal. This is a model that we use in practice. In practice, for some reason, we decided to drop x2, and if you drop x2, this is the coefficient that we can estimate for the beta 1. We call it beta tilde 1, okay? Don't confuse the tilde versus hat. So hat is the ideal one, tilde is the one that we did in practice. Okay, now we want to say something about unbiasedness of this beta tilde 1. And as we talked about it last class, the problem with this red shaded area is that it is contaminated with error terms. And how do I say that it's contaminated with error terms? Because, let me actually do it by sequence. Oops, sorry. You see, this red shaded area here is going to have, some of them are here, right? Think of these green dots. It belongs to x1 as well, but it used to belong to x2. Can you see that? So this means that this part is correlated with this part. Now I'm calling this new part because if I drop x2, what will happen to all these green dots here? They will go to the unobserved factor. I call them u here. Now the problem is that your x1 and u are correlated. The correlation is not 0 anymore. So this is a violation of assumption number 4. So I don't have, so this is violation of MLR4, or I cannot say expected value of u given x1 is equal to 0 anymore. So we don't have it. Okay, and if I don't have this, the assumption, so what can I conclude? Beta tilde 1 is biased. In short, what does it mean it's biased? It means that, x1 is contaminated with some error term. It's not a good news. So x1 is endogenous variable here. And if it is endogenous, your coefficient is going to be biased. So what does bias mean? It means that something like this. The number that you're calculating here, that's not the true number. It's either inflated by the effect of x2 or deflated by the effect of x2. We're gonna see which one is the case. So it depends on a couple of things that we have to mathematically first go over it and then see what will happen. So we already answered the question of unbiasedness. If we have underspecification in the model, if we are dropping x2, which happens to be relevant from the model, then the bad news is that beta tilde 1 is going to be biased, and this is very bad news. We never wanted, having a biased estimator in the model, you cannot do anything with that. You cannot increase the sample size. You cannot do anything. If your coefficient is biased with the sample size of 10, it's going to be biased with the sample size of 10 million. Okay, so it's a very bad news. So we have to make sure that our model is not underspecified. And sadly or realistically, we can never guarantee that the model is not suffering from underspecification. The best we can do is say, okay, let's control for enough variables and hope that the coefficients are unbiased. Okay, so that's one thing. Now let's answer the second question. Remember, we're interested in two questions. Number 1, unbiasedness. Number 2, the variance. Now let's see what will happen to the variance of beta tilde 1. So let me one more time write down the equation for variance of beta tilde. It's going to be sigma squared SST x1 1 minus r squared 1. Okay, so here in this example, because if I drop x2 from the model, this r squared 1 is going to be literally 0, because if I regress x1 and nothing, it doesn't make any sense, right? So if you're not interested in that part, But what we can say is that, well, I want you to think about intuition. Intuitively, I want you to compare, let me use black. I want you to compare this blue shaded area with this red shaded area. You have already answered this question multiple times in the previous classes. Which one has a lower variance? The one that the shaded area is larger. So the beta tilde one, because OLS is using more information, we dropped x2, now this part belongs to x1, right? It's using more information now, and that's a good news for the variance, because the more information you use, the variance is going to decrease. However, in beta hat one, we're using less information. Look at the blue shaded area here. So the variance is going to be larger. So we can say the variance of beta tilde 1 decreased, and we are happy. Do you see what's the trade-off here? So if I drop x2 from the model, so in sum, if x2 is dropped, we have two effects, bad news and good news. The bad news is that beta tilde 1 is biased. The good news is that because we use more information, then the variance of beta tilde 1 is smaller. And there's always, in econometrics, there's always trade-off between the two. So if you drop one variable, you're making the other variable bias the coefficients, but the variance of that coefficient is going to be smaller. So again, if you ask me which way should I go, there's no clear-cut numbers or general rule, but in my opinion, you should go with the model which is, so if you want to compare these two, which is unbiased. So between model number 1 and model number 2, I'm going to prefer model number 1, even though the variance of beta hat 1 is larger than the variance of beta tilde 1. But it's unbiased. I know I'm hitting at the target, but if the variance is a little larger, I really don't mind, because I can fix the variance thing by including more observation. If I increase the sample size, the variance is going to decrease. But if I increase the sample size, the unbiasedness, the bias does not go anywhere. So that's a really important issue I want you to think about. All right, now let's quantify this thing. Again, intuitively, we kind of know what we're talking about, but let's see mathematically, how can we quantify that? Okay, so as a reminder, this is your true model out there. And let me actually write it down. Y is equal to beta 0 plus beta 1 x1 plus beta 2 x2 plus u. However, we are going to say, let's drop x2. But this x2 was relevant and was related to x1. And it was related to x1, so we can rewrite x2 like this. If I regress x2 on x1, I can write it like this. x2 is equal to delta 0 plus delta 1 x1 plus b. Guys, do not get stuck in these are just names. I can call it beta, I can call it gamma, I can call it alpha, okay, whatever. Here, as a convention, we just use delta, right? Basically, if I regress x2 on x1, then we can think of it as, okay, there's a constant, let's call that constant delta 0 plus, there's an intercept, let's call it delta 1, then x1, and everything else we're going to call it, let's say unobserved factor, because u is reserved for the original model, let's call it nu, okay? This is nu, or I don't know, you can think of it as v, but it's nu. All right, now I know that this is the variable that I'm dropping from the model. Let's see what will happen to the new coefficients if I drop that. So let's replace this x2 by this equation and rewrite the whole thing. So y is going to equal to beta 0 plus beta 1 x1 plus beta 2 x2. This is my x2, right? And then plus u. Now let's do the multiplications and rewrite the formula even further. So what do we have? Beta 0 plus, let's let's put all the constants in one side and the intercepts in the other side, right? So let's factor in for all the for the constants. So beta 0 is a constant, beta 2 multiply delta 0 is also a constant. So I'm going to add them and stack them here. Beta 0 plus beta 2 delta 0. This is going to be my new intercept, or we call it beta tilde. Okay. Now let's continue. I have beta 1 x1 and beta 2 delta 1 x1 and beta 2 new. So let's factor in the x1 and then rewrite this thing. So what I have beta 1 plus beta 2 delta 1 multiply x1. This is my new slope, or beta tilde 1. And whatever is left, we just call it a new error term. So this is my new error term. Again, I can call it anything. I can call it, let's see, what did we call it in the previous slide? Well, actually, we didn't give a name because here we wrote the hat version and tilde version. You can call it anything. Let me call it gamma, whatever. Okay. So as you can see, if I drop x2 from the model, then this is going to be the new model. There's a new intercept, there's a new slope, and there's a new error term. We are not interested in the intercept and slope, intercept and the error term. What we care about is the new slope, right? So first, all estimated coefficients will be biased. So what are we talking about? We're saying that the beta tilde 0 and beta tilde 1 are both biased. And how do I know that? Because what was the definition of unbiasedness? If the expected value of beta, well, the one that you're estimating, beta 0 is equal to beta 0 if, and expected value of beta tilde 1 is equal to beta 1 if. Is that the case here? No, because when I calculate the expected value of beta tilde 0, what is it? The expected value of, we have to open up this one, right? Let's rewrite it. Beta 0 plus beta 2 delta 0. This is not equal to beta 0. Actually, it's going to be equal to beta 0 plus beta 2 expected value of delta 0. So it's not equal to beta 0. So it's going to be biased. So this beta tilde 0 is biased, beta tilde 1 is biased. We're going to calculate, again, we're not really interested in the biasness of the intercept, but for the slope, because it changes our interpretation, we're interested. So let's do that in a separate slide. Okay, what is the bias of beta tilde 1? Guys, again, as a reminder, go back. We know that this thing is biased. Using a Venn diagram, clearly we know why it is biased, because the correlation between x1 and u is not 0 anymore. x1 is endogenous. Going back to slide, let's quantify this bias. Okay, the expected, let's see if on average we are hitting at the target. Let's see if beta tilde 1 on average is equal to beta 1. If that's the case, we call it unbiased. Otherwise, we call it biased. We know that it's going to be biased, right? So expected value of beta tilde 1. What was beta tilde 1? Going back to the previous slide. Oops, sorry. Going back to the previous slide. This is my new beta tilde 1, right? So beta 1 plus beta 2 delta 1. But we are dealing with the estimated versions. So it's going to be expected value of beta hat 1 plus beta hat 2 delta tilde 1. Okay. Again, this delta, I could use a delta hat, but the textbook just used delta tilde. It really doesn't matter. Okay. The point is that it's estimated. Then what can I say? We are using the properties of expectation. It's going to be expected value of beta hat 1 plus expected value of beta hat 2 multiply delta tilde 1. We know that in the true model, the expected value of beta hat 1 is equal to beta 1. How do I know that? Because going back to the whiteboard, we already talked about it. If I have x1 and x2 in the model, beta hat 1 and beta hat 2 are going to be unbiased. What does it mean? Expected value of beta hat 1 is going to be beta 1. Expected value of beta hat 2 is going to be beta 2, right? So I know this for a fact. So we know it, fact, right? So this means that expected value of beta hat 1 is going to be beta 1. And then expected value of beta hat 2, I know it's going to be equal to beta 2. And multiply delta tilde 1. The point is that this is not equal to beta 1. Because if it is not equal to beta 1, then our beta tilde 1 is going to be biased, right? And how we calculate the bias? Simply say expected value of beta tilde 1 minus beta 1, and it's going to be your bias. In this case, the bias is going to be beta 2 delta tilde 1. Okay. Now, what I want you to take away from this couple of slides is not to memorize all these equations and derivation, but think of the intuition. So at the end of the day, if you have one variable in the model which was relevant, and if you drop it, if I drop x2, it's going to make my coefficient of beta hat 1, which is now called beta tilde 1, biased. And that bias depends on two things. So that's what I want you to take away. The bias of your new coefficient is going to depend on two things. What are the two things? Beta 2 and delta 1. Or delta tilde 1, delta hat 1. What was beta 2? Beta 2 was the effect of the variable that you're dropping from the model on y, so effect of x2 in this example on y. Delta 1 was the effect of x2 on x1. So this is the thing that I want you to remember. So if I give you, we're going to look at a real world example and things are going to make a lot more sense, but bear with me for a second. But so for instance, if I tell you we're dropping x3 from the model, what will happen to the bias of x2? And I will give you some scenarios, right? What are you expected to know is that you have to be able to calculate the sign of bias. If I drop x2, is the bias is going to be positive or negative, right? The positivity and negativity of that bias depends on the sign of beta 2 and delta 1. Okay. In the textbook, there's a nice table which summarizes the bias of beta tilde 1 when x2 is omitted from the model, right? And as we said, it depends on two things, the sign of beta 2 and the sign of delta 1. What was delta 1? If I regress x2 and x1, right? This is the representation of my delta 1. And do you agree that this has something to do with the correlation between x1 and x2? At least the signs are the same. If the correlation between x1 and x2 is positive, delta 1 is positive. If the correlation is negative, delta 1 is negative, right? So let's work with the correlation between x1 and x2 and the sign of beta 2 from the other side, okay? At the end of the day, you need to figure out what is the sign of these two things, and then if you multiply them by each other, you get the overall sign. So for instance, if beta 2 is positive, correlation is positive, we have a positive bias. If beta 2 is positive, correlation is negative, we have a negative bias. If beta 2 is negative, correlation is positive, we have a negative bias. If the beta 2 is negative, correlation is negative, so negative, negative, positive, right? So the direction of the bias is something very important. And now let's go ahead and use one real world example, and hopefully everything is going to make sense. And I will tell you what I expect you to take away from these slides. Okay, let's look at a real world example. We are omitting ability in the wage equation. So we're regressing wage on education and ability. But in our data, in the Woolridge data set, there is no variable called ability, okay? So what does it mean? It means that you know that this is a true model, or at least this is the model that you're interested in, but practically you cannot use that model. You're gonna end up with this model. Wage is equal to beta 0 plus beta 1 education. Now, because we did that, we want to see if this number has a positive bias or negative bias. How can I do that? Again, I'm omitting ability. So I have to figure out, I have to tell you something about two numbers, beta 2 and delta 1. Beta 2 was the effect of the one that you're omitting, in this case ability, on the wage, right? So what is the effect of, I want you to think of the signs. What is the effect of ability on wage, positive or negative? It's going to be positive, right? Because the more capable you are, most probably the wage is positive, right? Okay, so we're done with the sign of beta 2. What about the sign of delta 1? And we said that, you know, for simplicity, let's think about it as a correlation between x1 and x2. What is x1 here? Correlation is education. What is x2? Ability. So what do you think of correlation between education and ability? Most probably this is also positive, okay? So the correlation between education and ability is positive. So your delta 1 is positive. The correlation between ability and wage is positive. So beta 2 is positive. So if I multiply positive by positive, so the bias is positive. So positive bias. This is what I want you to be able to do. If I give you a question and I say that, okay, let's drop this variable, what will happen to the coefficient of the other variable? So you have to make an argument like this. You have to take control for two things, beta 2 and delta 1. And again, these are just some numbers. It can be beta 12 and delta, I don't know, 10, whatever. But when you look at the equation, it makes more sense. So I want you to think about it like this. If abilities drop, what will happen to this one? What was the relationship between ability and wage from one hand? What was the relationship between ability and education from the other hand? And then you multiply these signs to each other to figure out what was the effect on beta 1. Was it a positive bias or negative bias? Okay. So in this case, the return to education beta 1 is going to be overestimated in this model. In this model, the number that you calculate at the end of the day, it's going to be overestimated. Why? Because beta 2 delta 1 was positive. It will look as if people with many years of education earn very high wage, but we know this is overestimated. It is partly true. Why? Because part of it is because of their ability. So we are not including that ability in our calculation. So for that reason, this number that you're reporting is biased upward or positively biased. Okay. All right. I want you to think about this question. When is there no omitted variable bias? Use a Venn diagram and think about it, and I'll give you the answer in the class. But basically, I just want to think about this one. I want you to think about this one. When there is no omitted variable bias. So y, x1, x2. Definitely, if I drop x2 here, the beta tilde 1 is going to be biased. So under which scenario, how should I change this Venn diagram in a way that if I drop x2, it doesn't make a variable bias? Okay, so think about it. All right. Now let's look at some numbers from the textbook. Actually, let's read through this example. Example 3.6. These are hourly wage equation. Okay, we are regressing log wage on education and ability. And we know that, again, suppose, we're always making assumptions. Suppose that assumption MLR1 through MLR4 is satisfied, right? So it means that the beta hat 1 and beta hat 2 are going to be unbiased. However, the data set wage 1 in the Wooldridge does not contain the ability thing. So at the end of the day, you will use this equation and estimate the numbers. And these are the numbers. OLS is going to use that wage versus education for you and tell you that, you know, this coefficient was, what is it, 0.083. Okay. So 0.083, it means that if education increased by 1 year, the wage, because here we have log wage, right? The wage is going to increase by 8.3%. So what do we mean here that we have a positive bias? Because we already discussed that there's going to be a positive bias. This implies that the number that you're reporting at the end of the day, this is what you believe. You say 1 year increase in education will increase the wage on average. This is important. On average, the wage is going to increase by 8.3%. The whole idea is that this 8.3% has a positive bias. On average, this number is large, right? On average is, you know, because it contains the effect of ability in itself as well. If I were able to put the ability in the model, so if for somehow we were able to use a proxy variable, and let's ignore this one. So again, I don't care what is this new beta tilde, but I want to tell you something about education. If I were able to come up with a proxy variable for ability, let's say instead of ability, I use IQ. I can collect information on IQ, right? I said, let's use IQ as a proxy for ability and then add it to the model. Then on average, the number that you get here is going to be some number less than 0.83. So that's the idea. Because this is a total effect of education and ability here. But here, maybe let's say, again, I'm just making up some numbers, 6% here, 2% here. They don't necessarily need to add up to 8.3 because this is for one sample. If I use another sample, the numbers are going to be different. And this highlighted, the yellow highlight is basically talking about that. This is a result from only a single sample, one sample. So we cannot say that 0.83 is greater than beta 1. We have already talked about these things, right? So the true return to education could be lower or higher than 8.3, that we're talking about the beta 1, and we will never know for sure. Okay. However, this is important. This is the new thing that we discussed. We know that on average, we know that the average of the estimates across all random samples would be too large. We know that this number, 8.3, is positively biased. It's too large because it is basically somehow summarizing the effect of ability on wage as well. So if I put back that effect in the model and control for that, the net effect of education on wage is going to be less than 8.3. So that's the takeaway from the biasness. All right, so we're done with let's see, we're done with number 2, omitting a relevant variable. We saw what will happen to the bias. Well, yes, it makes it biased. Oh, sorry, what will happen to unbiasedness? It makes your coefficient biased, but at the same time it decreases the variance. So there is a trade-off between the two. And I told you that if I ever want to pick one, I will definitely go with a model which is unbiased. Okay. Even though the variance is larger. Okay, now let me pause the video here, and in the next video we're going to talk about how to deal with multicollinearity. We already know what is multicollinearity, but let's see how we can deal with that.